Welcome to section 5.1 for our abbreviated Corona class. Today we're going to work on finding the area underneath the curve, and in place of section 5.1 homework, I want to do this. So we're going to start by looking at this graph. Pretty uninspiring graph, just a constant function. Somebody traveling at a very brisk 180 miles an hour, as if they're driving in a Formula One car. And they're going to drive that fast for a total of 60 seconds. So how far would they go? Well, we'll go back to the old formula, distance equals rate times time. And if you're traveling for 60 seconds at 180 miles an hour, well, that's 1 minute. So let's convert that 1 minute to hours. So that's 60 seconds divided by 3,600 seconds in an hour. So you get 1/60th of an hour times 180 gives you a distance of 3 miles. So in other words, the area underneath this curve, 180 times 60, is proportional to how far you go, the distance that you travel. And that's great, as long as you're traveling in a constant speed. But what if you're not going in a uniform speed, a nice even speed? Say something like problem number 14, where for the first 10 seconds of this interval of time, you're going at 182.9 miles an hour. And then after 10 seconds, you're down to 168. And you keep on dropping, etc. And you have a pattern that goes like this. Well, here's the graph of that. And you can see the dots where we have our data. And I fit a polynomial to this to kind of fill out the graph in a nice continuous way, because you can kind of believe that a race car is not going to be driving around in a herky-jerky fashion. You're not going to drop instantly from 182.9 down to 168. Our goal then is still the same. We want to figure out, well, how far did this driver go in that short time? And we're going to approach this by trying to draw some rectangles underneath these curves and estimate the area. And that's not going to be too hard. It's just going to be basically some geometry, right? Rectangle, the area of a rectangle is just going to be length times width, or width times height, however you prefer to think of it. So we're going to click over to a Desmos link. And that Desmos link is here, or one version of that is here. And take a look at things there. So the idea here, when you get here, let me undo some of this a little bit. One thing that you might want to do when you get into this is click in the upper right hand corner. I'm not sure you're actually going to be able to see them in this graph, but click projector mode. That should make things a little darker. So if your screen's on the light side and you want to see things more pronounced, click projector mode, then click again. And here's our graph. So it's no longer a Google document. We got a nice graph of this. But what I want is I want to try and estimate the area underneath this curve. And we're going to do that in a couple ways. So the first way we're going to do that is with what are called left-hand rectangles. And this is the fun part. And even though you might be watching this alone, feel free to ooh and ah. So you're going to take this little slider here, click on it, and drag. Ooh, ah. And you see these rectangles that are growing from left to right? That's going to represent an area. And it's going to try and help us estimate the area underneath this curve. So we've got a total of 6 intervals. And we want to use that to estimate the area underneath this curve. So we're going to take these left-hand endpoints, which are our data points, and multiply them by the width of this interval, which is 10. 10 is in seconds. And then add up all these areas. And the sum of those areas should give us an estimate, not a perfect one, but an estimate of the overall area underneath this curve. And from there, we get the distance. So let's take out the TI-84 and do that. So what it's going to look like, it's going to be 10, which is the width of our interval, times 189 182.9 plus 10 times 168, etc. Well, this is going to get kind of tedious. And there's another thing. We've got to account for the fact that 10 is in seconds, and we have to divide by 3,600 to convert seconds to a fraction of an hour. So, but I think you get the idea here. We got to do all these multiplications and such. So let me just see if I can't take a shortcut here and look back at something that I've already put in. So I'm going to factor out that 10 from everything and just divide it by 3,600. So that gives me my time. And then here's my rates. I'm going to add up all these rates times time, and that gives me my distance. And let's see what that looks like. So notice I put this in for a total of our 6 points. And let me just kind of go through and let you see what that looks like. So here's all our data. One thing to notice, let's see, I should go a little bit further. Yeah, there. One thing to notice, I did not use the last point of our data set for our left-hand intervals. Why not? Well, let's take a look here. If we go back to our graph, we're using the left-hand endpoint, which is this one, not the right-hand endpoint, which is this one. So when we're finding these heights, we're going to take the height as being measured by the left-hand endpoint of the interval and multiply it by the width. Now, the width of all these intervals is 10, so we're okay there. But when we're using the left-hand endpoint to find this area, then you should be getting something from the left-hand intervals. And so there's 7 points of data. We're only going to use 6 of them. All right, let's shut these off. Shall I let you look at the answer here? Sure, why not? You should get something about 2.383, and that's one of 3 different estimates that we're going to get for how far this car traveled during that time. Let's go back to our handout here. So the first estimate we got was by using the left-hand endpoint to try and use that height, the left-hand endpoint, to find the height times the width, add them up, and we got an estimate of the area. How about if we use the right-hand endpoint? Is that going to make a difference? Well, let's find out. So the idea here is to take and bring that back down to 0 for our right-hand endpoint. Excuse me, for our left-hand endpoint. For our right-hand endpoint, well, let me grab that. Ooh, ah. I hope you remember that, right? Ooh, ah. Cool. So now notice that we're using the right-hand endpoints. So we're going to use that height right here and right here, all 6 of these, to find the area represented by these rectangles. You multiply the width by the y-coordinate of the height, and you're going to get another estimate of the area underneath this curve. Now, it's going to be a different estimate, right? Because, well, we're using different endpoints. And again, kind of like the first time we did this, notice that even though we have 7 data points, we're only using 6 of them. We're not using this point at all. Your summation should start here with that height times the width, and then this height times width, and so on. Difference between the last one and this one is also we're going to be using this endpoint, whereas we didn't use that in the last rendition of this problem. So that's going to give you a different estimate. You're going to have to crunch that out in your calculator. Then what? Well, then I want you to think about these estimates. I'm going to ask you a couple more questions to go over. The first one asks to go back to your left-hand rectangles. So to do that, I'll shut off these, go back to your left-hand rectangles. So here the height is coming from the left-hand edge. And I want you to look at the rectangles that we draw here while it's a decreasing function. So particularly right here in our second interval. Is the area underneath this rectangle an overestimate or an underestimate of the area underneath this curve? That is, if I was to calculate the area underneath this rectangle or in this rectangle and compare it to the area underneath this curve, would this be more or less than the area underneath this curve? And you can see that pattern again down here while it's a decreasing function. So the function is decreasing until somewhere around here, and then it starts increasing. So when the function's increasing and using left-hand endpoints, are you going to underestimate or overestimate the area underneath this curve? That is, if I was to calculate, say, the area in this rectangle right here, the fifth of our rectangles, how is that going to compare to the area underneath the curve in this interval between 40 and 50 seconds? So that's this part. How does the estimates compare, underestimate or overestimate when you have increasing and decreasing functions? Okay, so far you found the area underneath this curve by using the left-hand endpoints and the right-hand endpoints. You could get a third estimate, which is actually kind of a good estimate, by doing something else. What if we averaged these two? So if we did both of them and just took the average, and the average is going to be somewhere in the middle, and actually should be a pretty good estimate of the overall area. To get a glimpse of the overall area of what I would consider the true answer, and it's true within quotes, our polynomial that approximates this data is pretty good, but it's not perfect. But if you want to regard this as the true estimate, then you can do the following. Grab the slider for M after you've turned off the sliders for R and P. And yeah, more ooh, ah. Here we go. And that true area is about 2.3877. So how did your estimates do in comparison? And in particular, what can we do to improve those estimates? So I think that's one of the last questions down here. So you got the first estimate with the left-hand rectangles, the second estimate with the right-hand rectangles, average those two, and we get the true value, which one of those happened to be closest. Now, beyond just averaging things to try and get a better estimate, is there another way that you can improve the overall estimate? So if you stay tuned to the rest of this video, you might figure that out. Now, the last thing I want to know from you is, was this a good assignment? Did it help you to understand the area underneath a curve and how you can approximate that with rectangles? Let's kind of continue with one of your homework problems from section 5.1. So this is problem number 3, and I'll try and share the Desmos link here with you. I've modified this a little bit so that we're working with the correct function, which is 1 over x, and we're looking for the area underneath the curve between these endpoints of 1 and 2. You don't have to work with just those. I mean, this is really flexible. You can do 0.5 to 2.5, that kind of thing. But what we are really looking for is the area underneath this curve between 1 and 2. So let me reset those sliders, 1 and 2. And the problem asks us to use 4 rectangles. So that's why n is equal to 4 here. And the first part of the problem says, well, let's use left-hand rectangles. So you know what? If you want left-hand rectangles, according to this, then I got to set the slider down to 0. So can you see the difference? Now the height of this rectangle is being judged at the left-hand endpoint of these intervals. So we divided up the interval 1 to 2 into 4 parts, 4 equally spaced steps. And you can see the x coordinates of those steps. Let me see if I can't make that a little bit more spread out. Let's see. There we go. So these are the left-hand endpoints of our rectangles. 1, 1 1/4, 1 1/2, 1 3/4. And then you got the associated heights. The reciprocal of 1, of course, is 1. The reciprocal of 1.25 or 5/4 is 4/5, which is 0.8, 2/3, and then what would that be? It'd be 4/7. So you've got the heights here. And in using the heights, you could try and figure out an estimate of the area underneath this curve. Now just look at it. Do you think the estimate is going to be a good estimate? Is it going to underestimate or overestimate the true area? Well, I'm hoping that you reach the conclusion that it's a overestimate. Since these rectangles are taller than the graph, this is it's not going to be a bad estimate, but it's not going to be really good. So our estimate currently is about 0.7595. Well, the true answer here is going to be the log of 2. So let's just do that down here. ln of 2. How about 2 there? 0.6931. I don't think we're too close. It's not real good. So is there any way that I can make this a better estimate? I don't necessarily have to go to left-hand endpoints or right-hand endpoints to do that, but is there any way I can make that a better estimate? All right, tell you what. Let's look at the right-hand endpoints and see how that compares. If I choose right-hand intervals, now the height is going to come from the right hand of my 4 intervals, like that. And this time I think my estimate is going to be an underestimate. It's probably not going to be much better than my first one. So let's take a look here and compare this value to 0.69. And again, we're not doing so good. A kind of a compromise on all this would be to use the midpoint. And that's one of the choices here that you can use. If you set C equal to 0.5, then we're going to judge the height of our rectangles as the midpoint in these intervals. And that's actually pretty good. Let's take a look here. Yeah, with the midpoint, 0.69, yeah, we're getting 2 significant figures right off the bat. But what I want to demonstrate here is that you can do much better in estimating the area underneath this curve. We can do much better. So last chance. Can you think of anything that I can do that would make this little underestimate and overestimate a little bit better? Well, if you said increase the number of intervals, then bravo. Let me go back to our left-hand intervals, and let's slowly add rectangles. So we're going to increase the number of intervals. And to help see that, let me see if I can't spread this out a little bit. There we go. And let's slowly add some rectangles. Let's do this here too. I want you to see what happens to this number and see how close it gets to the log of 2. So as you add more and more rectangles, well, you get a couple significant digits anyways. And we're at 77 rectangles. This is the repetitive kind of stuff that a computer can do really, really good. That's what they were made for. And I don't think we're going to quite get down to 0.693. Oh, there we go. Yeah, that's not too bad. Notice we're up to 500 rectangles. So pretty good. And eventually, what's going to happen? Well, eventually what's going to happen is we're going to take the limit as n approaches infinity, and this will be not just an approximation, it'll be an exact value. And that's where we're headed. But right now, we got to understand a little bit about areas through these rectangles. Let's go back and take a look at things with a different method. Suppose we started out with, let's see, right-hand endpoints. This time, this should be an underestimate of the area. So let's see how this one does. We'll start out with 4 rectangles, and our sum is 0.6345. Let's see how that number changes as we add more rectangles. And, notice we're getting closer to 0.69. We're up to 200 rectangles. Still looking for that next digit. Will we find it? Will we find it? Not quite. Not quite. So true answer is 0.6931, and we didn't quite get up there. So, eventually though, as you let n approach infinity, you will get the exact answer of log of 2. It's something we'll be able to calculate for ourselves later on. Let's do one last one, and we'll reset our slider back to n equal 4 and take a look at things with the midpoint method. And I think the midpoint method is actually going to work pretty good here. Although eventually our goal is not to be looking at this with areas of rectangles. We're going to do something much better, and we're going to see that when we work on the fundamental theorem of calculus. So with n equal 4, this is pretty nice. The midpoint method, using the midpoint of my intervals to estimate the height, works pretty good. I've already got 2 significant digits. Let's see how those significant digits change as we increase n. And wow, look at that. With not even 40 rectangles, I've already got 4 significant digits. That's pretty good. That's really, really good. Okay, I hope this gives you enough to understand your assignment better. That is the handout here. And if you have any questions, please let me know. Also, give me some feedback on the assignment in the video. That'd be greatly appreciated. So, any more questions? No? Well, hey.
That was easy.
And see ya.